All right, so for this first one, we have that as part of his mathematics exploration about classical books, Jason investigated the time taken by students in his school to read the book The Old Man and the Sea. And they tell us he collected his data by stopping and asking students in the school corridor until he reached his target of 10 students from each of the literature classes in his school. What is now in yellow is this guy's sampling method, okay? So we need to state which of the two sampling methods, systematic recorder, Jason has used. All right, so this is one of the things you just kind of have to know. Um, Systematic, the way it works is like, let's say you have a population of 100,000 in a city, and you will choose that every 10th person, or no, let's say every 50th person, you interview them, okay? You interview, or that is like your sample, see? So that means you interview the person number 50, the person number 100, the person number 150, and so on and so forth. See, so that would be systematic. The key thing about systematic here is that it's every X amount of people. See? On the other hand, quota would be like, okay, of these 100,000, you sample or you interview the first 50. So then you would be doing person number one, person number two, person number three until you reach 50. See? That is the difference between systematic or quota. And so here, the key word or a big hint is that they say until. See? So until he reaches his target of 10 students per class, right, from each of the literature classes in his school, um, that is like his sampling method. See? And so since it's about reaching a certain amount, until is the big hint for quota, and it also strays from systematic because systematic would say something like every X amount of people. So in this case, it's not every X amount of people. It is until he reaches his target of 10 students. So that is for part A. Part A, the answer is quite simply quota. That is explanation. Then for part B, they tell us that Jason constructed the following box and whisker diagram to show the number of hours students in the sample took to read this book and to calculate the median time to read the book. All right. The big thing here is understanding how to read a box and whisker diagram. And so in any example, quite literally any example, this first line here is going to be your minimum, which hint makes the other line over here your maximum. Okay, so it's your minimum maximum values. What you have in between is Q1, Q2, and Q3. The other cool thing here that, well, doesn't show up in this problem, but it is good to know about box and whisker diagrams, is that the value like of having your data set up like this is that you know that between minimum and Q1, for example, this is the first 25% of your data. Between between Q1 and Q2, this is your second 25% of your data. See? And so that being said, and actually helping us for part B, this whole part here, if you add these two numbers, of course, the 25 and 25, whoops, you reach 50%. And so 50% is right at the middle. Right at the middle is going to be your median. Median is Q2, okay? Q2 equals median. And where is my Q2? Well, we look at our graph. It's on 10, okay? So that is for part B, all right? But yeah, so that was like a mini one-on-one on how to read box and whisker diagrams. And for the median, we just put Q2. Q2 is the thing in the middle, see? All right, for part C, they ask us to calculate the interquartile range. The formula for this is actually in your formula booklet. So if you don't recall it, please check there, get familiar with it. It's very important to get familiar with the formula booklet. It's one of the few things you will have when you enter the IB exam. The interquartile range, also called IQR, is going to be Q3 minus Q1. So Q3 in this case is right here, 15. Q1 is right here, which would be 6, 7. This right here would be 7. See? So 15 minus 7 is going to be 8. Your interquartile range is 8. Then they tell us that Mackenzie, over here, a member of the sample, took 25 hours to read the novel, and Jason believes that Mackenzie's time is not an outlier, and we need to see whether Jason is correct or not in respects to this. See? And so here a lot of people would say, all right, where the hell is 25? 25 is over here. 25 is very much to the right side. it's even the maximum. And some people would say, oh, it's so far away from my data, it's probably an outlier. And that's like their justification. See? The thing is, we can't solve this visually, unfortunately. See? Not in this case. There is actually a formula we have to use, a formula that you do have to memorize. It is not in your formula booklet, but it goes like this. For outliers, you can have outliers on the upper end, or you can have outliers on the lower end. See? Um, and to figure out what that upper fence or lower fence is, it goes like this. For the upper fence, and so for your upper fence, since we are looking at the right side of the diagram, we will be taking Q3. See? And so the formula goes like this. You take Q3 for the upper fence, you add to it your IQR, and you multiply only the IQR by 1.5. See? And so this will be like your frame of reference. Anything beyond that will be considered an outlier. So let's go ahead and plug in. Q3 we said was 15. IQR we said was 8. And the 1.5 does its thing, just like that. And this is going to give you 27. So that means that my upper fence, that I will now mark in red, is going to be literally there. See? So anything to the right of this 27 will be considered an outlier, right? And so the number we're looking at is 25, ¿cierto? So Mackenzie, our homie, took 25 hours to read the novel. But since 25 is less than 27, in other words, it's less than your upper fence, that means it is not an outlier. And so what was Jason saying? Jason was saying that Jason believes, ¿cierto?, that Mackenzie's time is not an outlier. That means Jason is correct. Effectively, it is not an outlier. In this case, they do not ask for the lower fence, but just so that you know, the intuition is very similar, ¿cierto? So instead of Q3, because in this case we're looking at the right side, now we're looking at the left side. So now we take Q1, and instead of adding, we will be subtracting. So Q1 minus IQR times 1.5. So this is just showing how to get the lower fence, helping you figure out what is an outlier. And over here, we have the upper fence for the outlier on the other end. ¿Cierto? Yep, that's pretty much it. Then they tell us that for each student interviewed, Jason recorded the time taken to read The Old Man and the Sea, measured in hours, and paired this with the percentage score in their final exam. These data are represented on the scattered diagram. And so on the y-axis, as we can see here, we have percentage on the exam. For the x-axis, which is in hours, we have time. See? That means, just so that we are all on the same page, that someone that took 10 hours to read The Old Man and the Sea got about an 80% on the exam. Someone that took, say, whatever this amount is, got around 70% on the exam. See? So that is how you read this diagram. Part E is asking us to describe the correlation. And so this correlation, let's remember that correlation is kind of like in which direction the data is going. And so there's two things we can like really talk about with correlation. We can say whether it's positive or negative, or neither, ¿cierto? And you can also say whether it's strong or weak. And again, neither. See? And so in this case, what we can say is that it is kind of like going down, right? How do I know it's going down? Because if I draw a line of best fit, if I try to, try to run into as many of these points as possible, it's going to be something like this. So we can say that the correlation is negative, but it's a little bit harder to say whether it's strong, weak, or neither. See, so the big point here, because it is worth 1 point for part E, is to say that it is a negative correlation. See? You can argue that it's strong or weak. In this case, for the answer key, it doesn't matter. It's very important that you just put negative. See? But for correlations, again, there are two things you say, whether it's positive or negative, or neither, and how strong it is. Then they tell us that Jason correctly calculates the equation of the regression line, y on x, for these students to be this. See? So this that I'm putting, well, in yellow, is the same line that I drew over here. Of course, not like to scale, but that's the idea, ¿cierto? So this line that I put in yellow is in theory the equation of the regression line over there, right? So he tells us that he uses the equation to estimate the percentage score on the final exam for a student who read the book in 1.5 hours. So let's remember, the confusing part here is what the hell is y, what the hell is x, ¿cierto? Because they do give us 1.5 hours, but where do I plug that in? Do I plug it into y? Do I plug it into x? If you do not recall, go back, read, take a moment, look at your diagram. X measured in hours, Y percentage score. Booyah. So find the percentage score calculated by Jason. That means if we're finding percentage score, we are finding Y, so Y stays the same, and we will be plugging in for X, just like this. And so when X is 1.5 hours, Y will be just around 96.49, which is the same as leaving it as 96.5%. Awesome possum for part G, they tell us to state whether it is valid to use the regression line y on x for Jason's estimate and to give a reason for your answer. So here, there's always a couple things you can say. But it's important to take this from the perspective of like, how much sense does it make? And so does it make sense that I'm able to estimate someone that studied for 1.5 hours? Let's see. My data has that all of these data points, ¿cierto? The person that studied the most studied around 25 hours, right? The person that studied the least studied around, we can probably call that 5 hours. See, I'm kind of eyeballing it, but the idea is that the one that studied the least was 5 hours, the one that studied the most was 25. And so 1.5 is like, dude, it's like way over here, ¿cierto? So it's a little bit off. My closest data point is around 3.5 hours away. It's a lot, ¿cierto? And so here you can say not reliable because it is too far away. Literally. One of the answers, or how you can put it according to the answer key, is that you can say outside the given range of data. Basically, here that I have in orange is the 1.5 hours. It's a little bit too outside of the data that I already have, ¿cierto? If it was closer, like maybe here, you could argue that you might be able to use it to estimate. But the moment it's outside of the range of data, you can already use it as an argument. See? So that makes it not reliable for extrapolation. All right. Awesome. Then they tell us that Jason found a website that rated the top 50 classical books. He randomly chose 8 of these classical books and recorded the number of pages. For example, book H is rated 44th, like this guy here, and has 281 pages. See? These data are shown in the table. So book A has 4,215 pages and is considered the number 1 book on the store. See? Or of all time, better said. So then they tell us that Jason intends to analyze the data using Spearman's rank correlation coefficient RS. And to be able to do that, we actually have to fill in this table here. And so this table here, you will notice that it also has number of pages, much like this guy here. It also has top 50 rating, much like this guy here. But the big difference is that now we are working with ranks. So you're ranking things. You're putting them in order. For example, the most clear, I'll just show it and it'll probably make more sense. For book A, you have 4,215 pages. Is this the one with the most amount of pages? What is the closest number to this? The closest number to this is that guy. ¿Cierto? And so the one with the most number of pages is book A. The one with the second most number of pages is D. So we're going to put a 2 over here. What about the third? Well, what's the closest number to 1,225? It would have to be 863. ¿Cierto? So over here we're going to put 3. And we keep going. What's the closest number next to that? It would be this guy over here. So that would be number 4. And now you get the idea. ¿Cierto? Whoops. 5, 6, 7, 8. So that would be for number of pages. See, that's like how you rank it, basically. And for the top 50 rating, now that we get the intuition of the previous one, we will see here that, all right, this one is ranked first, so it's going to be the first one here. This one is ranked second, so it has to be second here. There is no third, there is no fourth, but there is a fifth. And the fifth is the closest one to 2. That's the key idea. Fifth is closest one to 2, so we put a 3 here. Which one is the closest one to 5? The 7, so we put a 4 here. Closest one to 7 of these 4, 13. Ah, you keep doing that, it actually ends up like this. All right, so that is for part H. All right, then now finally, they ask us to calculate the value of RS. And so RS makes reference to Spearman's rank correlation coefficient, and you use that with line reg on your calculator. See, so I'm going to show it now how that works. So in your calculator, probably looking something like this, you will go to stat, and since we are calculating something, we go to calc, go down to line reg. See? So what is line reg asking for? It's asking for an X list, a Y list, and a frequency list is store reg EQ. For now, don't worry about it. See? But you need an L1 and an L2. So where the hell do I find that? Well, stat edit. Stat edit, these are my lists. As you see up top, we have L1, we have L2, right? And so for L1, it's just going to be this first guy over here. So this whole guy is going to be L1. And, well, you guessed it, the other guy is going to be L2. See? So I already did that. I put them in order. It's very important that they are aligned. 1 goes with 1, 3 goes with 2, 5 goes with 3, etc. See, so once you do that, you go back over here, line reg, L1, L2, blah, blah, blah. Go ahead and calculate. You end up with this. ¿Cierto? So you can see that my equation looks something like y equals 0.714, right? Plus 1.2, blah, 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 right? 2857. And so in this case, and depending on your calculator, it gives the R value right away. But your R value is going to be this guy here. See, it's going to be like the slope, whatever you want to call it. That would be the value of RS. So that is part I, ¿cierto? So boom, boom. And interpreting the result, well, basically, here you would simply say that the R value, or actually before I jump to the big conclusion, right? Let's first say that an R value of 1, okay, is perfect correlation. It's literally perfect correlation, all right? Plus or negative 1. For example, if you have something that goes like this, that would be perfectly positive. If you have something that goes like that would be perfectly negative. As you see, it is starting at corners, it is ending at corners, right? That is like the main idea that I'm trying to show. For perfect correlation would be on R equals to 1. So on R of around 0.7, right, that is pretty close to 1. So you could consider it as strong or moderate, see? And because it's 0.7, that means it's going upward. It's also positive, so it's not negative. So you would actually say that this is a positive slash strong correlation, right? And it's very important that you don't just leave it at positive slash strong. You say that it's positive slash strong between, and here goes the context of the problem, between number of pages and top 50 rating. See? And so there's two big points that give, two big things that give points here. The first is describing the correlation well, so you say it's positive or negative, and whether it's strong or not, and then you give the context of the problem. You say that this correlation is positive or strong between blah blah blah. So between my x and y, which we said was number of pages, and top 50 rating, that is for number 1. And for the second one, we have that the diagram below shows a circular clock face with center O, which is this guy there. The clock face minute hand has a length of 10 centimeters, it's this line here, and the clock face hour hand has a length of 6 centimeters, that is there. At 4 o'clock, we have point A and point B, which is what it says there. See? All right, so all the information that is given to us is already drawn into the diagram. It's always worth double checking that. Awesome. For part A, we have find the size of angle AOB in degrees. So when it says AOB like that, and it puts the little sign on top of the O like this, it means it is asking for this angle here. Awesome. So what the hell is that? All right, for part A, there's a couple of ways to solve this, and I'm going to choose an approach or a method that helps for what's coming. See, so part C is going to be very similar. Again, there's a lot of ways to solve this, but just to be practical and efficient, I'm going to show you this way. So, one of the ways you can approach this is to ask yourself, all right, so from my origin to, let's say, 1, how many degrees is that? From my origin to, let's say, 2, how many degrees is that? And is there a way I can make a formula to find that out consistently? Well, one of the things that we know is that from here to here, it's 90 degrees because it's a right angle, ¿cierto? From here to here, it's another 90. From here to here, it's another 90. And the last bit is also 90. You add those four 90s up, you have 360 degrees. So 360 degrees is what goes around the circle. See? That's why when people say do a 360, you go around in a circle. Wow. Anyways, moving on. Point is, a circle, when you go all the way around it, it is 360 degrees. So, if we're trying to find the angle at 4, ¿cierto? We can go by whole numbers, right? So if I figure out how much angle I have when I reach 1, I can keep going until I reach 4. See? I know it sounds a little bit weird. It's going to make a little more sense in a second. Point is, if you take 360, which is the total amount of degrees of a circle, you divide it by 12 because we have 12 numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is going to be a big hint. See? So 360 divided by 12 is going to give me 30. So what does this mean? Because I divided by 12, it's telling me that at each one of these, like, whoops, that didn't work out as I expected. At each one of these numbers, you have 30 degrees. So from here to here, I have 30 degrees. From here to here, I have another 30. From here to here, I have another 30, etc., until we reach number 4. See? And so here I have 4 30s. So I have 4 times 30. It's going to give you 120. So part A is 120 degrees, and that is the method. See? The biggest thing I want to show right now, and as you see that it's color-coded in green, I divide by 12 because there are 12 numbers. Okay, keep that in mind. For part C, it's going to be very helpful. Got it? So that is the approach for part A. For part B, we have find the distance between points A and B. So that is making reference to between A and B, it would be this right there, right? And well, technically B is, oh well, yeah, it would be just that from here to here, see? And we have this angle here, 120. So we have a triangle that looks something like this. We have one angle and two sides between that angle, see? Now, that's an important word that you just said. We have two sides between an angle. Whenever that happens, you have to think of trigonometry and a certain rule, a certain formula, okay? Point is, if you're trying to find the missing side, which is this one here, ¿cierto? What are the tools that you have? Pythagoras theorem, if it's a right triangle, or trigonometry in every other case. So we open up our formula booklet, we go to the part of trigonometry, and we see what we can use. I've explained this in a lot more detail in my other videos, but as you see, the sine rule works in pairs. See? Remember that little a and big A makes reference to the following. You have big A being the angles, and little a being the sides. Okay, so just to make it more visually appealing, it would be something like this. See? So right now we have a triangle where we have two sides in between, right? So let's say A and B. Whoops, that's little b. And we're missing little c. So that's when the cosine rule kicks in. See? I cannot use the pairs here because I don't have enough matching pairs to plug in like this, but I can use the cosine rule in every other case, right? So I know the cosine rule looks kind of nasty, but just trust it and follow what it says. See? So what it's saying right now, right here, is saying, okay, you need to put the side that you don't have, the two other missing sides, which is what we have here. ¿Cierto? The two other missing sides are there. So that would be A and B. The 2AB, I have it as well. And cosine C is the angle of your missing side. I'm going to say that again. It's the angle of your missing side. It's the angle of your missing side. So, bada bing, bada boom, we can use the cosine rule. All right, I know I explained that a little bit fast. In some of my other videos, I go a little bit slower. But just so you know, that is the formula I'm using. I'm going to put it in my other monitor, but just trust me, that is what I'm doing. If you go ahead and plug it in, it's going to look something like this. You will have that AB, which is right here, ¿cierto? A to B, squared equals 10 squared plus 6 squared minus 2 times 10 times 6 times cosine 120. See, so I'm just following what the formula booklet was telling me. You solve this, you end up with AB being equal to 14. Do not forget the units, centimeters. All right, so that is for part B. See, nailed it. We keep going. Also, before we keep going, this is worth 3 points. So one of the points is, showing some sort of work. The other point is probably using the formula. And the third point, which is why I'm talking about this in the first place, is the units, okay? Sometimes the units can be a whole ass point. Don't forget it. It's important. So it's also worth looking at how many points the answer is worth. As a quick reminder that, hey, put your units, see? So yeah, don't forget. Cool. Here we have, for part C, between 4 o'clock and 4:13, right? So right here, it's going to be 4:13. The endpoint of the minute hand rotates through an angle theta from point A to C. Awesome. That is illustrated in my diagram. So I need to find the size of the angle theta in degrees. Now, if you recall a little bit from part A, right, we divided by 12. So take a moment and remember, why did you divide it by 12? You divided by 12 because there were 12 numbers here. So you took that 360, divided by 12, bada bing, bada boom. You figured out that every time you hit one of these big numbers, it's 30 degrees. That was our strategy. Our strategy here is very similar, but slightly changed. We still have 360 on top because there are 360 degrees going around, but my denominator is going to change a little bit, right? And so in this case, I can't do it by 12 because this value that I'm trying to find here isn't aligned with any of the big numbers, see? So what you actually have to do is align your formula with the little numbers. What do I mean by this? I mean by 401, 402, 403, 404, 405, 406, 407, 408, 409, 4010, 4011, 4012, 4013. So if I keep going, adding all of these little, whatevers, you're going to notice that there is a certain amount of them. See? From here to here, I have, dang it, why does that not work? From here to here, I have 5. From here to here, I have another 5. See? I'm talking about the minutes. So how many minutes are there in this whole clock? There are 60 minutes in this whole clock because it is showing a whole hour. ¿Cierto? So if you go ahead and do that, this is going to give you 6. That means that for every minute, this angle here is 6. Which is no different than when we said that for every big one, we have an angle of 30. It's the same thing, just that way smaller now. See? So I have 6, right? So this is like 6 angles per minute, if you want to think about it. It's a weird way to put it, but intuitively, I'm sure it makes sense. So you get 6 angles per minute. Since we're talking from 4 to 4:13, that is 13 minutes. Bada bing, bada boom, theta is going to be equal to 13 times 6. Theta is equal to 78. That is part C. For part D, you need to calculate the length of arc AC. So, first of all, what the heck is it even saying? When it talks about length, it's going to be a sort of distance. And when it talks about arc, well, an arc looks something like that, ¿cierto? So it's going to be talking about this arc here. It's that distance. First, I will talk about a common mistake, then I will show how to solve it. A common mistake here is to say, well, this is a triangle, ¿cierto? It's not a triangle. A triangle would be what is drawn in green right now. An arc has a sort of curve to it, so now it's not a triangle anymore. It is indeed an arc. Okay, how the hell do you find the length of an arc? Well, thankfully, and once again, we have our formula booklet. It's very important that you get familiar with this guy. Okay, when you have your test, the IB exam, you're going in with your brain, your pen and pencil, a whole lot of confidence, and the formula booklet. Okay, you gotta get used to the formula booklet. The formula booklet has length of an arc and area of a sector. Right now we're looking at length of an arc. Okay, it asks for the angle, the length, and r, which is radius. Okay, pi is, well, you know what pi is. It's in your calculator. Don't worry about it. See? So that is the formula that I'm using, just so that you know. So for part D, using that formula, I'm just going to write it out real quick so that we are all on the same page. It looks like this. So I'm going to plug in theta, which we found out from part C is 78, divided by 360, times 2 times pi, r, which is radius, it's this guy here, times 10. All right, so whatever that is for part D. So length is going to be, trust me on this, just about 13.6135. All right, awesome. And because it is a length, we can, or a distance, we can put the units as well. That is for part D. For part E, calculate the area of the shaded sector AOC. So again, formula booklet, look at that, area of a sector. So now you're starting to realize, okay, this part is pretty easy, right? Well, the hard part, or the complicated thing, is understanding how the formula works, and also keeping in mind that this is actually a formula booklet. See, I feel like a lot of times people miss points just because they're not familiar with the formula booklet, and I think that is something that you can very easily, learn or fix or whatever. That it? So area of a sector, as I just showed you, looks like this. Theta divided by 360 times pi r squared. This big A represents area. See? So I'm just going to go ahead and plug in, right? So the area of my sector is going to be equal to the theta that I defined, which was 78, divided by 360 times pi times r squared, we said was 10. So I plug all of that into my calculator, and you end up with just about 68.0678 centimeters. Small detail, it's not centimeters just like this, it is centimeters squared. Quick tip, if you're talking about distance, it's going to be to the power of 1, right? Which you usually don't even write. If it's area, it's going to be to the power of 2. If it is volume, it is going to be to the power of 3. So yeah, rule of thumb. Awesome. Then they tell us that a second clock is illustrated in the diagram below. The clock face has a radius of 10 centimeters with a minute, and hour hands both of length 10 centimeters. So from here to here, it is 10. From here to here, it is also 10. The time shown is 6 a.m. The bottom of the face is located at 3 centimeters above a horizontal bookshelf. And so those 3 centimeters are depicted right. Dang it. I don't know why that doesn't work. They are depicted right here. Those 3 centimeters. Awesome. F, write down the height of the endpoint of the minute hand above the bookshelf at 6 a.m. And so the height for part F of the endpoint of the minute hand, so it's this guy here, above the bookshelf, so the bookshelf being here, it's going to be this whole height. See? So this whole height is going to be the 10 plus the other 10 plus the 3 down here. So all of these added together will be 10 plus 10 plus 3, 23. Do not forget the units, centimeters. That is part F. Later on, they say that the height h in centimeters of the endpoint of the minute hand above the bookshelf is modeled by the function blah. All right, so that is for the function where theta is the angle rotated by the minute hand from 6 a.m. And to find the value of h when theta is equal to 160. So all we really have to do here is, well, plug in theta equals 160 and find the value for h. So h when theta is 160 will be this. 10 times cosine of 160 plus 13. It's literally that. So h1 theta is 160 is going to be 3.60307, do not forget the units, centimeters. So again, part G was simply just plugging in. All right, and then for part H, they tell us that the height, G in centimeters, of the endpoint of the hour hand above the bookshelf is modeled by the function blah. See? So very similar to what we had in part G, but now we have a new function for the hour hand, and they tell us that theta is the angle in degrees rotated by the minute hand from 6 a.m. And for part H, we need to write down the amplitude of G. So what the hell is amplitude? Let's start with that. Amplitude is the following. And all of these sine, cosine, and tangent functions, you have something that goes like this. Visually, it's pretty much always like this, and it's never ending. See? And so the amplitude is something that cuts right through pretty much the middle, or so to say. And it's going to be the distance from like that middle to the minimum and that middle to the maximum. So both of these orange lines that I just drew, they are both amplitudes. See? They are both amplitude, and that is the idea of amplitude. See? So some of the other examples could be maybe here to here, here to here, etc. It's very important that it's from the middle to a maximum. See? It's also important that these are the same value, right? They have the same distance covered. So, that being said, let's go back to H. We need to write down the amplitude of G. So you can figure this out manually, or you can do it really quickly just by knowing like the general sort of form of the cosine function. And so the cosine function, whatever is in front of the cosine or sine is always going to be your amplitude. So this, in absolute value, is going to be your amplitude, always. Quite literally always. And so absolute value makes anything turn positive. For example, absolute value of -4 is going to be 4. Absolute value of -7 is going to be 7. Absolute value of a already 7 is just going to be 7. See, so whatever is negative turns it positive. So you get the absolute value of whatever is in front of your cosine function, and that's going to be your amplitude. So in this case, you can literally just say, yeah, the amplitude is 10. Bada bim, bada boom, you're done. You can also do it manually, as I was saying earlier, which is just by graphing, finding out the minimum, finding out the maximum, and finding like the difference between the two, dividing by 2, right? Now that was a lot of blah blah. Let's see it in action. Here I have decimals. You can do it in your graphing calculator. I'm just going to show it here because it's a little bit faster. But as you see, here I have this minimum here with the point 0, 0,3. So let's say here is 0, 0,3. And we have this guy here, which is 12 pi, comma 23. See? So this point here is going to be 12 pi, comma 23. So point is, what is this distance here? Like this whole height? This whole height has to do with this 3 and this 23. So if I do 23 minus 3, that's the whole height. See, it's 20. So that means the whole thing in red is 20. So how much is each of the blues? Well, 2 blues give 1 red. So 20 divided by 2 gives me 1 blue. See? And 1 blue we said was 10. Same amplitude as here. So that's how you find it manually. And the sort of quick way is by, something they show you in class. It's not in the form of booklet. But more importantly, if you know what amplitude is, you can figure it out. So you can graph it, work from there. So that is the more important part here. So amplitude is effectively from this middle to the maximum or from this middle to the minimum. It's that distance. Do not confuse it with the whole height. Common mistake. Moving on, we have the endpoints of the minute hand and the hour hand. So it's the minute hand being, this guy here, and the hour hand being that guy here. At some point they meet, see? And they meet when theta equals k. So, of course, we need to find the possible value of k. Smallest possible value of k. There's a couple ways to approach this, and what I consider most intuitive is the following. This is the one for the minute hand. This is the one for the hour hand. And so if you go ahead and equal them to each other, that is going to be wherever theta equals k. quite literally. See? So if I go ahead and equal them to each other, we will have h theta, which is the minute one, right? Minute one, being equal to g theta, see? Which is the hour one. Why do we do that? Because we are trying to find whenever the minute hand and hour hand meet, see? So that is why they're being equal to each other. I'm going to go ahead and plug in and see what happens, see? So if I go ahead and do that, I will end up with something that looks like 10 times cosine theta plus 13, which is this first guy here, equals negative 10 times cosine theta divided by 12 plus 13. See? So this is h and this is the g. See? So I need to do this and end up with theta equals something. See? Now whatever that theta is going to be the value that I want. However, many people at this stage get very confused on what to do. See? You can use cosine inverse. There's a couple of different ways to solve it. But I think that especially when you face a problem that you're not sure how to solve, like which functions to use, etc., to get your variable alone, you can always use the calc intersect trick. See, I have a whole video that explains it in depth, but basically you're gonna call all of this y1, you're gonna call all of this y2, you're gonna do calc intersect, and whatever that intersection is the value that makes this thing true, which is making them equal to each other, which is what you're trying to find, ¿cierto? Whichever value of theta makes this equal to each other is what you're trying to find for this last part, part I. So let's see it in action. Let's not make this just blah blah. Y1, as I said, is going to be this first one that I already put. So negative 10. I'm just going to rewrite it so that we're all on the same page. Negative 10 times cosine theta. Theta, I'm just going to put it as a variable. All of this plus 13. Y2 is, oops, sorry, this first one is not negative. Apologies for that. The second one is negative. We have negative 10 times cosine parentheses fraction theta divided by 12 close parentheses, all of this plus 13 as well. And we're going to go ahead and calc intersect. See, so calc intersect, see what happens. So there's one of my functions. There is the other one. All right, and so now once we do the calc intersect, we will notice that the calculator is asking for three things. First of all, it's asking for what is your first curve. As we can see, this first curve is the one that has, well, the more curvy parts to it, right? So we're gonna agree to our calculator with that. Our second curve we can see is the long one, which is the hour hand, right? Because it increases in height much more slowly. So yes, we agree with our calculator. And now it asks for guess. Now the purpose of guess is to ask your calculator which intersection you want, right? So if I put guess over here, it's going to give me that intersection over on the right side. Now the big question now is which intersection do I want and which one is actually the smallest. So intuitively, all of us would say, well, whatever is most on the left is the smallest, right? So I'm going to go ahead and pop it over here, and we get an answer of 166, comma, 3.29, right? Now, let's hold that thought for a second. Go for the one that's right next to it, and the one right next to it is 196, comma, 3.4. Now, it's always very important to interpret the context of your answers, right? And so, for example, this first one, which I will now draw in, let's say, blue, right? Is telling me that when the minute hand reaches an angle of 166, which would be around here, right? We're going to have the minute hand going like that. So I'm just going to mark MH for minute hand. It will be at a height of 3.29. So the 3.29 is shown here, right? And this intersection goes to show that the hour hand, which as we saw in our graph, grows much more slowly, right? Will be somewhere around, let's say here. So this would be the HH, my hour hand, and it will also have a height of 3.29. So what's in blue right now is my first intersection, right? Wherein, although they have the same height by this 3.29, right? They're not on top of each other. And what we're trying to find over here is whenever the endpoints of the minute hand and the hour hand meet each other. You have to keep in mind that all of these functions we're working with the idea of height in mind, right? And so although these have equal height right now, the context of the problem does not tell me that they are actually on top of each other. They will be on top of each other later on, which I am going to mark in, let's say, orange, right? So later on, when it reaches 196 degrees, which is going to be, I don't know, way over here, right? Maybe there. My minute hand is going to be here, and my hour hand as well. And so the answer actually is going to be 186, 3.4. Essentially, and this is probably one of the hardest problems of at this level, right? The context matters way too much for this problem, and you have to keep in mind that this is all in terms of height. See? So although the height is the same, the visual diagram is always going to be helpful. The fact that they have the same height does not necessarily mean that they are on top of each other. In the second scenario, they are. See? But in the first scenario, they are not. How do you know this? Because the minute hand right now is behind the hour hand. See, the minute hand is trying to catch up to the hour hand. That means that at 2 points in time will they be the same height. Once, as I saw in blue, and another time as we saw in orange. In blue, they have separate heights. In orange, they have the same height because they are on top of each other. So, that being said, that is how you solve number 2. All right, and now for this third one, we have the Daisy, right? Invested 37,000 Australian dollars in a fixed deposit account with an annual interest rate of 6.4% compounded quarterly. They ask us to calculate for part A the value of Daisy's investment after 2 years. All right, so there's a lot of buzzwords here that can help indicate how you should approach this problem. If you start hearing words like annual interest rate or compounded quarterly or the word compounded in particular, you immediately need to think of compound interest, okay? And in your formula booklet, you're gonna go to it, find compound interest, and work with that. So all of the following parts of this problem use compound interest a lot, so let's get very familiar with it. Compound interest, this is the formula, see? It is asking for 5 things in order to use it. It asks for FV, future value, PV, present value, N, number of years, K, number of compounding periods per year, and R, the nominal annual rate of interest. Okay, this is a lot of blah blah. Let's go into the intuition of it, okay? So first of all, your approach for any kind of compound interest problem is first to define those 5 things. See, so those 5 things, as we said, was FV, PV, N, K, and R, which we know is in percent. Okay? So in every single one of these exercises, you will be missing one. Okay, I'm going to say that again. You will have 4 out of 5 of these, and the last one is the one that you're going to try to find. All right? So let's first see what we have. Well, they tell us that they invested this amount. So that is going to be my initial value, my present value. Okay? So 37,000 will go right here. They tell us that it has an annual interest rate of 6.4%. So my R is going to be right there. They tell me that it's compounded quarterly. So quarterly in quarts, that means in 1 year I have 4 quarters, right? K is the number of compounding periods per year. I have 4 periods per year because it is in quarters. So K is going to be 4. And N is the number of years they ask us after 2 years. See? So as we can see, our variable, our X, is going to be FV. So as I said, we have 4 out of 5. ¿Cierto? The one that we're missing is FV. So what we can do is simply plug in to the formula, which is this one here, okay? And see what happens. So FV stays as FV. PV we said was 37,000. Parentheses 1 plus the R, which was 6.4, divided by 100 times K, which we said was 4. All of this to the power of K times N, which is basically 4 times 2. See? All right. So if you plug all of that in, you're going to end up with just about this number here. And since we are answering to the nearest dollar, we will change this to 42,010 as my answer. See? Now notice, this is worth 3 points. So one of the points is using the formula correctly, another point is followed through, etc. And lastly, do not forget the units, AUD. Okay? So that is for part A. Again, the big idea I want you guys to have in mind is that you will always be missing one. Okay, so you need to identify which one you're missing and work from there. Okay, so that is for part A. For part B, they tell us that after M months, the amount of money in the fixed deposit account has appreciated to more than 50,000 AUD, and to find the minimum value of M, where M is that. So for this next part, we need to identify what we're missing and what we have. ¿Cierto? Always keep in mind the 4 out of 5 thing. So now what we're missing is the M months. See? So it's kind of like the time period thing that's going on. We still have it quarterly, so this number does not change. But now we don't know how for how many years or also for how many months. So this is now going to be my new variable. We're just going to call it M as they ask for it here. ¿Cierto? After M months. That is the variable that we're missing. Or just to be practical, I'm going to put it as X. See, so that is my new X. Okay. My future value, right, is going to be a little bit different because now we know that it has appreciated to more than 50,000 AUD, right? And so appreciated means that it increased in value. Depreciated, decreased in value. So my FV is now going to be 50,000. My present value remains the same because it's still the same investment. And everything else stays put. See? So essentially, I still have a 4 to 5, but my values change a little bit. See? So now I'm going to be plugging in FV over here, right? So I'm going to have 50,000 over here. And I'm going to be changing this 2 to a variable. We're just going to put it as X. See? So this is my new out of 5. This is my new 4 out of 5 that I'm working with. This is now the variable that I'm missing. And now I need to find the value of X. Also, small detail, but here it says find the minimum value of M. See? So as the months keep going, my investment, which is basically like this, ¿cierto? Is going to get bigger over time. And so the value of X that I'm trying to find will be in this mode here. ¿Cierto? So as long as it passes 50,000, we need to find how many months that is. See? But it can't be less than 50,000. All right, so you write this inequality. That is already a whole point. And now in order to solve this inequality, there's a couple ways to approach it. My favorite is the following. There is the calc and intersect trick. I do have a video on this that goes much more in depth, but basically I'm going to call this y1 on my calculator. I'm going to call this y2 on my calculator. Calc intersect, whatever makes it work, wherever it intersects, is the value of X that I'm trying to find. And so we will approach it that way. So y1, we're going to call it 50,000. And y2 is the whole thing on the right side. See? So I'm going to have 37k times 1 plus fraction 6.4 divided by 100 times 4, close parentheses, to the power of 4x. See? So I'm going to go ahead and graph. It's probably not going to show up in my window. That is okay. When this happens, of course, press window. I mean, try to make sure that it can fit into what you're trying to see, right? You have to see the intersection in order to use the function called intersect. You can play around with the window. What I like to do is use zoom, scroll down to 0 and press zoom fit. Zoom fit tends to nail what you're looking for, tends to get the intersection at the very least. So we give this a moment. we can see that there's one of my lines. The 50,000 is probably the one on the bottom. Just to make sure, we're gonna check here. All right, so Y max, we're gonna call it 55,000, and there it should show up. Let me play around with this a little bit more. Apologies. It's probably not going to be that many months. I'm going to change my X max. And there's the intersect. See? All right, so that was a little bit time consuming, but I think it's also worth showing that you do have to play around in this part. Okay, you have to play around with the window, play around with its zoom, and make sure that you can actually see the intersect. Once you can see the intersect, it does not have to look pretty, but it has to be able to show up. You press your first curve, it's the one that's 50,000, which is Y1. Second curve, the one that's on the left, enter, and now we have guess. See? Guess is really just to ask your calculator which intersect you actually want. In this case, it's only 2 lines, so it doesn't matter. There's only one intersect. And we get that value there. See? So we get the value of 4.7, give me 1 second, 423, comma 50,000. So what that's telling me is that whatever makes these two equations equal to each other is when x, this guy here, is equal to that. See, so whenever that happens, these two equations are equal to each other. That means that if x is anything greater than this, it will be greater than 50,000. All right, that's the intuition of our approach. And we are not quite there with the answer because it is asking it in months. See, it's asking it for m in months and also m being that. Now, what the hell is that? M being this makes reference to m being a natural number. Okay, so m has to be part of natural numbers. That is kind of how you change this to words. M has to be part of natural numbers. And what are the natural numbers? It's considered 1, 2, 3, 4, 5. So any whole numbers that are positive. Okay, awesome. Now that we're talking about this, might as well cover integers. See, integers is another that's very common. It looks like a z, and that includes the negatives. Okay, negative whole numbers and also positive. All right, natural numbers tends to include the zero as well. So I have to give my answer in positive whole numbers. That's basically what it is, and also in months. And so this number right here is in years. See, so 4.7423 years. Well, we're gonna go ahead and take that number, multiply it by 12. Why 12? Because there are 12 months within a single year. And we end up with 56.9. All right. And so because we need to give our answer whole numbers, giving the answer is 56 is not enough, because at 56 I still have not completed this inequality. But at 57, it is beyond 56.9. This is the right amount of months, or the minimum amount of months, better said, in order for this part B to be true. See? So part B is simply going to be 57 months. This is the approach. If you have doubts how you can show your work here, how I wrote it here works perfectly. See, so you define y1, you define y2, you signal that you're going to use calc intersect, you get full credit. I did it in the IB exam, I got full credit. You can trust me on that. See? Awesome. Later on, they tell us that Daisy is saving to purchase a new apartment. The price of the apartment is 200K. And Daisy makes an initial payment of 25% and takes out a loan to pay the rest. See, so she pays part of it, like immediately, and the other part of it, she takes out a loan to pay the rest. So what is the amount of the loan? Well, the amount of the loan depends on how much she paid initially. And so 25%. All right. Quick percentage class. See? So percents, for example, 100%, if you write it as a number or a decimal, it's going to be 1. Okay? That means that 50% is equal to 0.50. Ah, interesting. So 25% is going to be 0.25. Cool. Why is this helpful? It's helpful because now we can take that 0.25, multiply it by 200,000, and find out what is 25% of 200,000. You put this into your calculator, you're going to find that it's 50,000. Awesome. So this is the initial payment, okay? The loan is whatever is left after the initial payment. That it? So if the initial payment is 50K, we're going to do 200K or 200,000 minus 50,000, and that is going to be the amount that she pays on the loan. The rest, ¿cierto? 150,000. Do not forget the units, AUD. That is the approach for part C, and we move on. So this same loan is for 10 years, the one that is 150,000 AUD. It is compounded monthly, important detail, with equal monthly payments of 1,700 AUD made by Daisy at the end of each month. So she took out this loan, she got her apartment, she has to pay off the loan, etc. See? So for this loan, we need to find the amount of interest paid by Daisy and the annual interest rate of the loan. So here you have to get a little bit familiar with like the language, like what the hell is even interest in the first place. Point is, the loan she took that she has to pay is 150,000 AUD. See? Now the bank has to make money out of this, ¿cierto? So there's a certain amount of interest that she has to pay, like sort of additionally, in order to, you know, so that the bank makes money, etc. Blah blah. And so simplifying in a lot of ways, we can say that because it's for 10 years, and because it's monthly, so 10 times 12, and because it's 1,700 per month, this minus the loan is the amount of interest that Daisy is going to pay. See? And this difference here, which is going to be a positive difference, ¿cierto? Is the amount that the bank basically gains. That it? Awesome. So, if we go ahead and do this, trust me on this, on your calculator, you're going to end up with 54,000 AUD. Okay, I might have gone a little bit fast in this part here, but point is, the interest paid, ¿cierto? Is going to be for 10 years, monthly, that's why it's 12, 1,700 per month, and we subtract this of the loan, which is from part C. That it? That is how the numbers showed up in the first place. That is part D, part I. All right, and now for this next part, we have that for this loan, we need to find the annual interest rate of the loan. Now, a very common mistake here that people do is that they keep working with the compound interest formula. And unfortunately, because we're talking about a loan, we are now talking about an annuity, which is something a little bit different. So basically, whenever you're talking about loans or something with equal monthly payments, this is probably the biggest hint I can give you. You are not going to use the compound interest formula anymore. You're going to use the finance app on your calculator. All right, so this is a big hint for using the finance app on your calculator. If we go ahead and open it, it will be on this apps button that's in purple. We press finance. And there's a lot of things here going on, but you will go to TVM solver. Okay, this is usually the one you're going to always use. And there's a couple things going on. See? So big N is now the amount of compounding periods. And so if before, for example, for monthly, we had that K was 12, and 10 years we had that N was 10, big N, right, which is the one up top over here, big N is now actually going to be a combination of both. Okay, it's the compounding periods, like all the amount of periods, it's going to be 12 times 10. Okay, so big N in this case is going to be 120. All right, so that's with the first one. I% is the interest rate, which is actually what we're trying to find. Whenever there's something you're trying to find using the finance app, you will leave it on 0. It will make a little bit more sense in a second. For PV present value, right, we are talking about the present value of the loan. And because it's a loan, it actually goes in as negative. So we have negative 150,000, sorry. PMT makes reference to these equal monthly payments, and so we know that each month or each period, better said, it's 1,700. So we're gonna go ahead and plug in 1,700 here. FV we will leave at 0, and PY/CY makes reference to the compounding periods and compounding years that are going on. In this case, we will leave both as 12. So that being said, we are almost done. What you need to do now is go back up to interest, because it is the one thing that you're missing, right? The one thing that you're trying to find in the first place. And you will go alpha enter. So alpha enter actually gives you the thing called solve. And so the calculator with all the other stuff that you inputted is going to give you the last thing that you're missing. Okay, so the intuition of the 4 out of 5 thing I was talking about earlier is still given here, just that what you're missing is the annual interest rate. And instead of plugging in and using calc intersect, you were plugging into the finance calculator. Again, you press alpha enter, boom, it solves it for you. It gives you that. See? And so within the missing variable, the calculator figures it out for you, and you get, let me just write it down real quick. 6.45779. Same thing as writing 6.46%. How do you show your work? You show your work by writing that N is 120, that PV is this, that PMT is this. You basically write what you put into your calculator. If you want to mega make sure that you're getting full credit, you can even go apps, finance, and write this, and you're gonna get full credit. Okay, trust me on that. But anyways, that is part D double I. All right, so for this part E, right, we have that after 5 years of paying off this loan, Daisy decides to pay the remainder in one final payment. Why would he do that? Because it's cheaper, you have to pay less interest, etc. So for part E, we need to find the amount of Daisy's final payment. The approach here is the following. Again, using the finance app thingy-majingy, we need to see what happens, or what is my future value in this case, after 5 years of paying off the loan, right? And so 5 years after paying the loan is how many compounding periods? I'm talking about big N. How many will it be after 5? Well, if after 10 it's 120, I can just take 120 divided by 2, and that will be after 5 years. See? So that's one approach for figuring out what big N is. The other approach is saying, okay, well, 5 years, and we have that it's monthly, right? So 5 times 12, that also gives you 60. See? So 2 ways of getting the same answer. Whatever. Point is, you put 60 up here. Everything else is already plugged in. And now we will find what my future value is. See, so I'm going to go alpha, enter, get that solve, and we end up with that. So the amount of Daisy's final payment has to be 86,973 AUD. Awesome. So this is how much she still has to pay for the final payment. See? Nice. For part F, we need to find out how much money Daisy saved by making one final payment after 5 years. And so the first thing we have to figure out is see how much Daisy has to pay in interest in total, and compare that to her paying everything right now immediately. So here we have to go a little bit back in time. If we see here for part D, part I, we have the amount of interest paid by Daisy. Back then, we figured out the amount of interest paid by Daisy was 54,000. Okay? And the loan was, as we can see over here, 25%. The amount of the loan was 150,000. Stay with me for a second, it's all going to come together. So the amount of the loan was 150,000. The interest she has to pay was 54,000. That means that in total she had to pay 150K plus 54K in interest. She had to pay 204K. See? So this is the amount she has to pay in total. But because she paid earlier, she actually saved some money. So how much money did she save? Let's find out. We subtract this number to the following amount. We first put this guy here, ¿cierto? Because it's what she paid. She already paid after 5 years. So we're going to be subtracting by 86,973. And we also subtracted by the next 5 years. See, and so the next 5 years, how much would it be? It would be 60. Why 60? Because of the 60 over here, times 1,700. Why 1,700? Because she pays 1,700 per month. So that being said, you go ahead and calculate that. You end up with 15,027 AUD. I think the hard part here is noticing that you need to find out this number, 204,000. And understanding that you have to subtract both things over here. See, not just one of them, it has to be both. So that is for number 3. Alright, for this next one, we have that the stopping distances for bicycles traveling at 20 kilometers per hour. This is per hour, just gonna make a quick hint here. When it's written with h to the power -1, anything to the power -1 is just gonna look like that. It goes to the bottom, goes to the denominator. So this is actually 20 kilometers per hour. Okay, it might look weird, but that's how it's written. So anyways, the stopping distances for bicycles traveling at 20 kilometers per hour are assumed to follow a normal distribution with the mean this and standard deviation this. So under this assumption, find correct to 4 decimal places the probability that a bicycle chosen at random traveling at 20 kilometers per hour manages to stop in less than 6.5 and in more than 7 meters. So in the world of normal distributions, you need to open up your calculator and look at the tools that you have. So first of all, because you are in the world of distributions, you're going to go to this blue button here, the one that's on top of vars. See, so I'm going to put second vars, so I hit that distribution button, and these are the tools that I have. Now you will pretty much always work with the first 3, okay, and it's important to be familiar with what these 3 things do. Now that being said, I have some notes on distribution that, if you want to take a screenshot or whatever, I suggest that you do. But basically, this is what each of these tools allows me to do. Let me find a little more space. These are the 3 main tools. See, so we have normal PDF, normal CDF, inventory normal. You can pause, take a second and read. The point is, in this case, we have to use normal CDF. See? So CDF, we use it whenever we have a range. All right, and so the range here, for example, in less than 6.5, it's going to be negative infinity until 6.5. That is going to be my range. See? And so normal CDF here makes sense. At the same time, you do not have to memorize what each one of these tools does. If you want to, you can. But I think it's far more important to understand that, A, you face an over distribution, you open up the distribution tab, ¿cierto? You look at the tools, you remember that the first 3 are the ones I use, and you go one by one, see which one fits. For example, normal PDF, what does it ask? It asks for an x value. It is not asking for a range. It will give you the probability of a single x value. See? And so here, since it's less than 6.5, it is a range. Normal PDF does not work here. We keep going down our list. Normal CDF. See? Whoops. I'm still in PDF in that scenario. Let me try again. Now we're on normal CDF. See, so now we have a range, we have lower, upper, the mean, the standard deviation, etc. What I just showed you is the correct approach if you do not remember which function you have to use, which is, fairly common. See, but play around with it, get familiar with the calculator, and recognize what you need in what scenario. Here I have the ranges, right? And so as I said, the lower one was going to be negative infinity. Your calculator writes it like this, which is -1 E99. And just to prove a point, this is basically like, it's like -1 million. Okay, that's the best way I can explain it. It's just a very, very big negative number. You do not have to write it like this whenever you want to put it manually. Just to prove my point, I'm just going to put -1 with a lot of zeros behind it. So that is sort of like signifying negative infinity. Upper, we said it was 6.5. So I'm going to put 6.5 here. This thing there is for median. For mean. We said that mean was 6.76. 6.76. And this other symbol here is going to be for standard deviation, which we said was 0.12. So we go ahead and paste. Boom, we end up with that number. So that number there is, I'm just going to write it over here, going to make a little bit of space. 0.12. 151 30 blah blah blah. See? Awesome. Now in this case, it has to be correct to 4 decimal places. So that means I will count my decimal places one by one. 1, 2, 3, 4. That means that on this fourth one, I need to look at whatever's right next to it and see if I round it up or down. Because it's a 3, I just leave it as it is. So it stays as that. That is the answer for this first part. If instead of a 3, we would have had, say, a 5, my answer would have been this. Okay, so that is how the rounding part of it works. Yeah, that is for this first part. For this second part, it's pretty much the same thing, just that in the other direction. See, so instead of in less than, we have more than. And so again, I open up my distribution. We go to CDF because it's a range. And now my lower is actually going to be 7 because it is 7 to positive infinity, right? Anything more than 7. Whoops, apologies for that. Ba-ba-ba. And my upper, instead of putting negative a million like the other time, I'm just going to put positive a million. See? And that should do the trick. Basically, you're asking your calculator like 7 to a very big number. See? 7 to positive infinity. It all works, right? My mean stays the same. My standard deviation does as well. Go ahead and paste. We end up with that. So that is 0.02275. And so now, a little bit like I was telling you earlier, 4 decimal places, right? So we have this first one, this second one, this third one, this fourth one. This 7, I have to compare to what's next to it. And look at that. It's a 5. So what does that mean? It turns into 0.0228. Awesome possum. So that is everything for part A. For part B, we have that 1,000 randomly selected bicycles are tested and their stopping distances when traveling 20 kilometers per hour are measured. Find correct to 4 significant figures. So now we're in the world of significant figures, not decimal places. The expected number of bicycles tested that stop between blah and blah. So again, we have a range. So that should already be telling us, okay, we are using CDF. So, whoops, distribution, CDF. We said it was going to be 6.5 and 6.75. That's my lower, that is my upper. Everything else remains the same. All right, so I end up with 0.451 663. So now, since we're talking about significant figures, the way significant figures works is that when you enter the realm of like decimal places, that means anything to the right of 0, your first significant figure is your first legit number, your first non-zero, or so to say. So this would be my first significant figure, my second, my third, and my fourth. So just like before, we look at this 6, my fourth significant figure, see what's next to it, see if I round it up or down. In this case, I round it up. I end up with 0.4517. All right, awesome. We are almost done here. Why are we almost done? Because it is asking for the expected number of bicycles. See? And so here I am actually getting, I'm getting a decimal, I'm getting a percent. And so a little bit of context that maybe would have cleared up also part A a little bit. Part A is probability. See? And so basically you're looking at this normal distribution. And in this case, I am looking at, well, knowing that the median is at 6.76, I am looking at 6.5 and 6.75. See? And so the number that we just got, which I'm going to highlight in yellow, see, is actually a probability. So this right here has a probability of 0.45, which is the same as a probability of 45%. Okay? So point is, there's a 45% chance that you pick a randomly selected bicycle that has a stopping distance between 6.5 and 6.75. All right? Now in this case, they aren't asking for probability anymore. They're asking for the expected number. And so what is the expected number of bicycles in this case? Well, if there's a 45% chance that I pick it, and we are picking 1,000 of them, let's take that 45%, multiply it by 1,000, which is the same as taking this 0.4517 and multiplying it by 1,000. So that is, for like expected numbers or sort of say, we end up with 451.7. So this is expected number of bikes right there. The biggest part we have to understand is that the first step is finding probability, and the second step is finding the expected number. So very, very careful. If it says expected number, do not forget that is what you're trying to find. See, you are not finding probability anymore. You're taking it one step further. For the second part, it's pretty much the same. We will go to distribution, CDF, because we're talking about range. My lower is going to be 6.75, as mentioned earlier. My upper will be 7. Everything else remains the same. Boom. We end up with that number there. So here we have 0.51045. We'll put the 6, why not? Alright, so in respects to significant figures, a common mistake that people do, and this is what I was trying to explain earlier, but this is a better example now, is that they think 0 is not a significant figure. And so significant figure is the first number that is not a 0 that shows up. For example, and I think this is going to leave it very clear, if I ask you for two significant figures of, let's say, this number here, your first significant number is not this 0, it is this 1. See? So this is your second significant figure. You compare it to this, you end up with that. Okay? So your significant figure does not count the 0. However, if I were to have a very similar scenario, and I have it like this, and I say, hey, do this to two significant figures, sure, you don't count this one, but you do count this one, and you do count the one after that. Okay? So two significant figures here would actually be that. All right? So there's this whole thing of when do you count the 0, when do you not? You do not count the 0 if you have not run into your first legit number yet. See? So in this scenario, we already ran into our first legit number. That means that this 5 over here is going to be my first significant figure, this 1 the second, this 0 the third, this 4 the fourth. See? Since it's correct to 4 significant figures, that means I take this 4, compare it to the 5. Because it's a 5, I round it up. So I end up with 0.5105. Again, this is in percent. The expected number is going to be this multiplied by 1,000, because we are looking at the expected number of bicycles. 1,000 randomly selected bicycles, that's why they 1,000. We end up with just around 510.5 bicycles. So that is for the second part. Bada bing, bada boom. Then they tell us that the measured stopping distance of 1,000 bicycles are given in the table below. So this is what was observed. Okay, that's a keyword here. This is what was observed. So less than 6.5 gave us 12. Between 6.5 and 6.75 gave us 428. Yada, yada, yada. See? Cool. Then they tell us that it is decided to perform a chi-squared goodness of fit test at the 5% level of significance to decide whether the stopping distances of bicycles traveling at 20 kilometers per hour can be modeled by a normal distribution with mean, blah, 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 standard deviation, blah, blah, blah. So, part C, state the null and alternative hypothesis. So, for the null hypothesis, I'm just going to put a text here, actually, it's going to be way easier. For the null hypothesis, for part C, okay, we're going to say that H0, in this case, has to be that the stopping distances can be modeled by n. Actually, I'm going to draw that next part. Can be modeled by, let me erase this, make a little bit of space for my homies. Can be modeled by n, parentheses, 6.76, comma, 0.12 squared. All right, so that is like the big thing for getting a point in this part of the problem. Because it's making reference to a normal distribution, right? Whether it can be modeled by a normal distribution, you have to write it how it corresponds. See, and so that's like a hard part here. The normal distribution, you put like a fancy n, the parentheses you put the median, and next to it you put the variance, which is standard deviation squared. Okay, so this is actually variance, see? Which again, as I said, variance is standard deviation squared. That's why you have the 0.12 squared over here, okay? So that is kind of like where they try to catch you in this part of the problem. So anyways, HO is going to be, it's generally what the exercise gives you. HO is generally going to be what the exercise is looking for. And that, in the sense that you're trying to see if it can be modeled. Okay, so here we're going to put can be as well. And then for this next part, we're going to put that H1 is basically the opposite of that. So stopping, whoops, that was a little loud. Stopping distances cannot be modeled by the same thing. See, so the same thing being n, 6.76, 0.12 squared. See, so as long as you're consistent in this sense, that h0 is going to be pretty much what the exercise gives you, and h1 is going to be the opposite of that by simply adding a negative. So we'd say cannot, ¿cierto? We end up with part C. For part D, we need to find the p-value for the test. Now, I can give you the answer right away, or I can give you like the approach, and I think the intuition of the approach is way more important. So here we are performing a test of chi-squared goodness of fit. See? Now that right there is a little more important than what you think. Goodness of fit. If we take the first letter of each, we end up with GOF. Aha. Might sound a little familiar, right? We go to stat test, because this is a test. We see which tests we have, and we find a chi-squared test. So a lot of people reach the chi-squared test and they say, booyah, I'm good to go. But it's goodness of fit, it's GOF. Scroll one more, there it is, GOF. What's the difference between the two? GOF is asking for lists. Okay. Chi-squared is asking for a matrix. These big letters with parentheses are a matrix, the other one is list. Here we have literally just one list here, number of bicycles. And so it makes sense that we use GOF because list. Basically, the intuition I'm trying to say is that GOF equals list. Not GOF, I don't know how else to put it, is going to be, well, you can say matrix or you can say not list, okay? So that's the intuition of when to use which. In this case, we are working with GOF. So, again, we open up our calculator, we see what it is asking for. Let's go step by step real slow. GOF, it asks for observed and expected. So my observed, as I said way earlier, is going to be right here. All of these is what was observed, not what was expected. As it says here, the measured stopping distances is what gave us here. See? So for observed, we have that table there, and now we need to find the expected one. The expected one is not given to us, but we can find it. So, writing down here, we have less than. Actually, maybe it's going to be a little faster if I just write it out. Essentially, we need to find, we have the range here, then the probability, and then the expected. Okay? So, the first range is less than 6.5. See? Then we have the probability of that, which we found in part 4.a, right here, less than 6.5, which was 0.0151. Okay? And my expected is going to be, well, 1,000, because it is the distances of 1,000 bicycles, right? Let me raise this a little bit so that we can all see and be on the same page. This is a chi-square test having in mind 1,000 bicycles. So my expected value is going to be 1,000 times my probability. See, in this case the probability is 0.0151. and that'll give me a certain value, okay? That certain value is going to be 1,000 times 0.0151, boom, 15.1, okay? So my expected table is now beginning to form over here. All right, so that is for less than 6.5. So that is the range, the probability is that, and my expected has to be, well, this whole thing on the right side, see? That is the approach, all right? The next range we said was between 6.5 and 6.75. So I'm just going to put, I mean, you guys know what's going on now, 6.5 and 6.75. What is the probability of that? We found it earlier in this part here. We said it was that number there. See? So that number there, simplified there, 0.4517. We're going to take 1,000, multiply it by that. We end up with roughly 451.7 bikes. And we keep going. The next range was between 6.75 and 7, which is part B right there. How convenient. I erased it by accident, but I recall that it was this. See? So this one is from here to here. The probability of that was 510. All right, at this point you must have realized what's going on. See? Again, we're doing this to build. Whoops, apologies for that. But yes, we're doing this to build the expected table. So then we can put the observed table and the expected table into our calculator, and we're good to go. And for more than 7, so it's going to be from 7 to positive infinity, we found it right there. See? We said that it was 0.0228. So here we're going to put 0.0228. Whoops, I missed a point over there. We do 1,000 times this, blah, blah, blah. We end up with 228, 22.8. All right, so this is my expected table. Just so that we're on the same page in terms of its intuition, we take the same ranges. See, so we take all of these ranges here, which are the same ranges that I have there. I find the probability of each of these ranges, which is from part A and part B. All right, awesome. All of these. And we find the expected value of this, expected being 1,000 bikes, because it's what the context of the problem is giving us. That's why we multiply by 1,000. And we generate the expected list there. See? So now we are ready to open up our calculator, go to stat test, scroll down to Goff, and observe expected L1, L2 respectively. So I need to go to stat now, edit. So stat edit, go to my list. Observed is going to be the first one. So I go ahead and pop those guys in. Expected is going to be the second one. I pop those guys in as well. And now we go ahead and actually do the test. Boom, boom, boom. df in this case is going to be 3. That is degrees of freedom. It's basically always going to be your rows minus 1, okay? Or your columns minus 1, depending on the context. In this case, I have 4 of them, so it's going to be 4 minus 1. Calculate. We end up with this. So the p-value for this test, part D, is going to be what we just got on our calculator, which is 0.0726 542. All right. So that is for part D. If you want to show your work, you basically put this window into your calculator, or you can also show all your work with the expected stuff. See? For part E, we need to state the conclusion for the test and give a reason for our answer. Now, in this case, we have a level of significance. Okay, so this is how we can see whether our answer is legit or not. Essentially, we need to compare this level of significance to our p-value and see what happens. So in this case, our level of significance, right, which is 0.05, is it greater than or less than our p-value? Well, our p-value is 0.0726542. In this case, our p-value is greater. So if our p-value is greater, and unfortunately this is one of the things you just kind of have to memorize, if our p-value is greater, then that means that there is insufficient evidence to reject HO. The other way that you can phrase it, if you'd like, is that you accept HO. All right? Either one of these works. Point is, you have to compare your critical value to your p-value, and this is the proper way to conclude it. So, that being said, that is part E. That is how you do number 4. All right, and now for the fifth one, we have that the cross-sectional view of a tunnel is shown on the axis below, where the line AB represents a vertical wall. That means this line over here. And look at the left side of the tunnel. The height in meters of the tunnel above the horizontal ground is modeled by this equation there from 2 to 8 relative to an origin O, this guy here. See? So essentially, this equation that they just gave us makes reference to this part of the tunnel. See? All of that part. All right, awesome. So for part A, well, the information they also give us is that point A has coordinates 2.0, so that means this guy here is that. Point B, which is this guy here, has the points 2, 2.4, and point C has the coordinates 8, 0. So this guy here is 8, 0. So the first thing is to find that, right? That being this guy here. And essentially that makes reference to the derivative of our function. So it's the derivative of the function y in respects to x. So the function of the derivative of the function y in respects to x, and they told us that the equation is this one here, right? So my equation is that. I need to do the derivative of that. So at the SL level, we will only be dealing with the derivative of a power. So that means, and I'm going to give an example on the left side first. If I have, let's say, x squared, and I do the derivative of that, I'm going to take the 2, pop it down up in front. So I'm going to have 2x. And up top, I'm going to subtract it by 1. So that means I end up with 2x to the power of 1, same as 2x. So the derivative of x squared is going to be this. Okay, that is just one quick example of how this derivative is going to work. That means that for this first term, once I do dy of dx, right, I end up with, for the first term, having 3 times negative 0.1, and my exponent is going to be subtracted by 1. See, so that is for my first term. For the second term, I end up with something kind of similar. 2 times 0.8 x to the power of 2 minus 1. That means that dy dx is going to be the same as negative 0.3 x squared plus 1.6 x. So that is for the first part of part A. Then we need to find the maximum height of the tunnel. So a little bit of intuition before we jump into it. This right here, when you talk about derivative, it is the same or very, very similar as rate of change. This probably sounds familiar. Slope. Okay, it's the same as slope. That means that, let's say if you have a slope of, I don't know, 2, which should be right here, it would be there. See? If you have a slope of maybe 1.5, it could be around there, right? And a slope of 0, and this is where it gets special, would be right there. Why is the slope 0 here? Because at any maximum or minimum of a parabola, the slope is 0. I'm going to write that out. The max of or minimum of any parabola has a slope of 0. Okay? And so this is very useful to know, especially when trying to optimize and find maximums and minimums, because that means that you can take whatever you had for your derivative and equal it to 0. What is that going to give me? That is going to give me the x value at my maximum. See? Again, you take dy dx, you equal it to 0. So that means I end up with 0 equals this. And I need to find the value of x that makes this true. See? Once I find that, that value of x is going to be this guy here. I plug that into my original function being this guy there, and I'm going to get the y maximum value. Okay? That is the game plan. Let's see it in action. In order to find what makes this true, this guy here, I mean, how to get x alone, there's a couple different ways you can factor, etc. For me, the most quick way for these kind of scenarios is always going to be graphing. It's just a personal choice, but there's a lot of ways to do it. See? So I'm going to put that y1 has to be equal to 0. So that's going to be this guy here. So this guy on the left is going to be y1. This guy on the right is going to be y2. I'm going to do calc intersect. See? So y2 has to be this here. We're going to go ahead and graph, see if it shows up in my field of view. It probably will not. I'm going to go to zoom fit down here, see if I can now see the intersect. And I can. See, so there's two intersects there, and we need to see which one makes more sense. So for the first intersect, we can see that it's at 0, 0. That does not help because it doesn't make sense given the context of the problem. This x value is definitely not at 0. I do calc intersect again. My first curve is basically my x-axis from y1, ¿cierto? And my second curve is the parabola thingy, which is this guy here. And now I pick guess. See? Remember that the guess function at this stage is to ask your calculator which intersect you want. Okay? Your calculator knows where the intersects are. The guess part of it is to tell it which intersect specifically you want. I want the one on the right side. We get this x value. See? So that means at this point here is going to be an x of 5.333. See? So if that is for my axis of symmetry, or like the x value of this guy up here, I just found out that the x value is this. Now I need to find the y value. See? To find the y value, I plug into my original one. See? And find out what it is. If I plug it into the other one, which is the slope one, I'm just going to find out what slope my function has when x is 5.333. See? If I plug in this 5.333 to the original one, I'm finding out which y value it has at that x. See? So, negative 0.1 times 5.333 continual to the power of 3 plus 0.8 parentheses 5.33333 parentheses exponent squared. That gives you that value there. So I have 7.585. And if I round it up, it's basically the same as 7.59. See? So 7.59 is, or this set of points better said, it is my maximum. And now that we found our maximum, do not forget the units that accompany it. This context of the problem is in meters. So for this next part, we would say that the maximum height of the tunnel is 7.59 meters. So all of that combined together is part A. For part B, they tell us that when x equals 4, the height of the tunnel is 6.4. So over here, we have 4, 6.4. And they tell us that when x is 6, the height of the tunnel is 7.2. Okay, so when x is 6, we have 7.2. All right, let's keep going. These points are shown as D and D on the diagram respectively, and to use the Trapezodial rule for part B with 3 intervals to estimate the cross-sectional area of the tunnel. All right, so at this stage, a lot of people are probably like, dude, what the hell is Trapezodial rule? Why is it asking in 3 intervals? What the hell is going on? So let's talk a little bit about why the trapezoidal rule is even used, its purpose, its intuition, etc. So lots of times in math, you are trying to find the area under a curve. See, that is why you use integrals in the first place. And in order to find the area under the curve, one way that you can do it is by splitting up your curve into shapes. What do I mean by this? You can make one shape here, another shape here, and another shape here. And so if you go ahead and add these three shapes, it is pretty close to the area under the curve. Yes, there is a little bit that we're missing, maybe here, maybe here. Of course, this is not trying to scale, but the idea is the same. I mean, you split up the area under the curve into a couple of shapes, and you add all up, and that can be a good hint of how much area is under the curve. So that is why it also asks in 3 intervals, because right now we have 3 shapes. Interesting. And now the trapezoidal rule is in your formula booklet right here, as you can see there. See? And now I'm going to explain a little bit the intuition behind it, how it works, etc. But just know that I am taking it from the formula booklet. This is something that you can check on your own. But the point is, it's up here. This A and B makes reference to my smallest and largest x values. And so, for example, my smallest x value for A is going to be 2. My smallest x value B is going to be 8. So, that being said, for h, right, we're going to have that h is 8 minus 2 divided by n. Now, n is going to be my amount of like shapes that I have, which also translates to amount of y values that I have. See? So these y values represent like certain trapezoids, or so to say. For example, a big hint that I can give right away is that y0 is my leftmost y value, and yn is my rightmost y value. So y0, for example, is going to be this guy over here, this 2.4, and my yn, right, this is y0, my yn is going to be my rightmost value or height of one of my shapes, which is going to be 0. See? So plugging in immediately, just to see how it ends up, we have 1/2 times h that I'm about to find out, ¿cierto? We have 3 down here. I'll show why it's 3 in a second, but we have 6 divided by 3 equals 2. H equals 2. So we have 1/2 times 2, parentheses, y0 we said was 2.4, plus yn we said was 0, plus 2, and now I'm talking about this part, see, 2 times y1, which we said was 2.4. Oops, sorry, not y1. That would be y0, apologies. Y1 would be the one after y0, of course, which is going to be this guy here, right? Given the shapes that we drew. So that's going to be my y1, which means that this one is going to be my y2. Awesome. So y1 is going to be 6.4 plus y2, we said is going to be 7.2. See? This 7.2 from there. All right, there is no y3 in this case, but there is a yn, which was just 0. See? Or I mean y3, yn, same thing in this scenario, it would be this 0 from there. All right? So that would be what we plug into our calculator, okay? This guy is a 3 because there are 3 y values besides y0 that I'm using. See, I'm going to say that again. Your n is going to be your y values besides y0. So we forget about this y0 for a second, and we count 1, 2, 3. That makes n equal 3. A common mistake here is saying that n equals 4, because, oh, you count the y0 as well. Not in this context. Okay, I know that's a little confusing. This is the kind of thing you just kind of have to memorize, but there it is. See? So you plug in this whole thing in green into your calculator, you're going to end up with just about 29.6, do not forget units, meters squared. So that is for the trapezoidal rule. All right, then now for this last part, we actually have to write down the integral, which can be used to find the cross-sectional area of the tunnel. And so this is awfully similar actually to what we wrote up here, right? For the trapezoidal rule, it's going to be very, very similar. But point is, as I said, an integral is used to find the area under a curve. Under which curve are we doing? We are doing it under that curve there. See? So you're actually going to do the integral from 2 to 8. Why 2 to 8? Because that would be from this 2 to that 8, which would of course be all of this area here. That's why it's from 2 to 8. So the integral from 2 to 8 of my original function, which is this guy here. We put dx at the end because it's, you know, the protocol of how you write integrals. But that would be c part I. All right, so this is just writing down the integral. It's not solving it. But the next part is actually solving it. See? And so for this next part, I could show you how to do it manually. But I get the hang that most of you prefer using your calculator for as many cases as you can. And I would share that intuition or that, you know, that energy. So I'm going to show you how to solve this integral into your calculator. For showing your work, you can just say, I used the calculator. These are the steps I used. But basically, you pull up your TI-84. And first, you go to y equals. You go to y equals. You plug in the equation that you want to do the integral of. So I'm going to go ahead and do that real quick. And for this next part, you're going to watch carefully what I'm going to do, okay? To open up like the integral function, okay, you're going to go to alpha, window. So alpha window, this little, you know, tab shows up. And you want to go to the fourth one. As you can see, it says fn int. That is stands for the function of an integral. So we open up the function of integral and boom, all we have to do is plug in. So here we will plug in from 2 to 8. Here, I guess in theory, you could put the whole equation. Just because of how I do it, I would go to alpha trace, plug in y1, which is the y1 that we just plugged in. This we define as y1, ¿cierto? And d of what? D of x. Enter. There you go. Awesome. I guess you could skip a step. I'm just going to show this real quick in case you didn't like the other method. You could, in theory, whoops, sorry about that. You could, in theory, go like this. You plug in directly over here. Put d of x. And it still works. Okay, so either method works, but point is you can do integrals on your calculator. That's kind of cool. I'm just saying. Point is this gives you 32.4. Because we are talking about integral, we're talking about area, we will be putting 3.4 meters squared. So that is the last part of part C, and that is the last exercise of this paper 2. I hope it helped. Take it easy. Remember, get familiar with the formula booklet. And, you know, you really are always more capable than what you think. Take it easy, homies.